But that which is worthwhile is not easily attained. Time to hit the books. Ready? 2 more weeks. Okay, so let's talk about orienting a surface. So you guys worked on parametrizing a surface, right? That was your little project for Friday, learning how to parameterize surfaces. So there's something called orienting a surface. And how many variables does it take to parameterize a surface in R3? 2, right? So we're describing every point, every ordered triple on the surface using 2 variables. That's what it means to parameterize a surface. Okay, so what about orienting a surface? So on each point of a surface, there are 2 directions normal to the surface. Would you agree with that?
Yes.
Equal and opposite directions are both normal to the surface, okay? So we say that a surface is orientable if one normal at each point can be picked in a continuous way. So in other words, the surface has 2 distinct sides. Okay, so if you can pick normals continuously, or if one normal at each point can be picked in a continuous way, that means there's really 2 sides to the surface. So, and then we call the direction of the orientation n. So then you choose. You say n is either this way or the opposite way. Make sure your brain is listening ahead of getting all the words written down. Okay, so this is what's called an open surface. This is an example of an open surface. And so this would be showing that the surface is oriented upward because I'm choosing my n vectors to be the ones kind of pointing generally upward, right? So the boundary, open surfaces have a boundary, and that boundary, what is the boundary between the 2 sides here? So how would you describe the boundary? What do you have to cross over to get from one side of the surface to the other? What kind of thing do you have to cross over to get from one side of the surface to the other? If you're an ant and you're walking around, you're on one side, what does the ant have to do to get to the other side, which is like the bottom? Cross over the edge, right? So the edge is like C, right? So like what I'm showing you is the actual part of the surface, then this. So we talked about closed curves that form the boundary of a surface. That would be C. So that would separate, that C would separate the 2 sides of the surface if you're talking about an open surface. So what's a closed surface? So a closed surface then is a surface that like has an inside and an outside. The surface kind of creates a solid, right? So there's like an inside and an outside. So here I'm showing the orientation of this closed surface as what, like outward orientation, right? Okay, so these are the 2 examples I'm showing here are perfectly good orientable surfaces. There are 2 sides of the surface. The first one, this open surface, has a kind of a top and a bottom, and I'm choosing the orientation to be upward. The second one is a closed surface, and then it has like an inside and an outside surface, 2 surfaces. I'm choosing the orientation to be outward, and those are conventional, right? So conventional would be upward is positive and outward is positive orientation of a surface. So what is a surface that's not orientable? So you guys know what a Mobius strip is? It's really cool. Like you take a piece of paper and give it 1/2 twist and then connect the sides again, you get a Mobius strip. And so why is this not orientable? So suppose I start here at point P and I assign the normal vector to be this way, okay? So then if I keep assigning n in continuous way, so here and then this is kind of back behind there like this, and then this is out like this. And then I would get down here and these would be up like this, right? Or actually coming kind of out at us. and then back here, and then back here, and then back here, and then what happens when I get back to point P? Now I'm going the opposite way. So I started with my orientation at P, and I continuously assigned these n vectors. When I got back to point P, it was not pointing in the same direction, it's pointing the opposite direction. So a Mobius strip, it's like only has one side. Do you see that? It doesn't have two distinct sides. So you can't assign n vectors continuously without leading to an ambiguity, right? So a Mobius strip is an example of a non-orientable surface. But this open surface, this is an example of perfectly orientable, and this closed surface that's orientable. Makes sense so far? Any questions on what we mean by orienting surface? Okay. So flux. What is flux? So we still have a few kind of things, a few ideas to build up before we get to flux, and that's the first one is an area vector. An area vector of a flat-oriented surface is a vector. We call it capital S. The capital S vector is called an area vector. The magnitude of that vector is the area of the flat-oriented surface. And then the direction of that vector is the direction of n. So what is n relative to the surface again? What direction is that? Normal to the surface. So yeah, so n, you can think of n as standing for normal to the surface. So a real easy example here. So I've got a 5×3 horizontal surface in R3 oriented upwards. What would the area vector be? What would the area vector be? Is that a vector? So the vector, so yeah, you got it. So the vector is, the magnitude of the vector is the area, and the direction of the vector is normal to the surface. So the vector is 15, right? 0, 0, 15, or 15K, right? You said 0, 0, 15, that's the same as 15K, right? 15K. Does it make sense? All right, so flux is the rate of flow of some vector field. So we have a surface and a vector field. So we're going to look at just what's going on at the surface in terms of the vector field F, and flux is a rate of flow through that. So you can think of kind of like a mesh or some kind of permeable, is that a word? Permeable kind of surface or something like that stuff can go through, right? And the stuff is modeled by the flow field. So flux is looking at the rate of flow through that surface of the flow field. So question is it cross product of F and S or dot product of F and S? So if I drew, say our flow is like this through this thing, so F is so, and then say right there. So I'm drawing vector field F. So are we interested in what? Are we interested in the amount of F that's parallel to S or perpendicular to S? Perpendicular to S? Parallel to S, right? S is already orthogonal to the surface. So what do we want? Cross product or dot product? Dot. Because S is already orthogonal, we want how much of F is in the direction of S? That's dot product, right? That's dot product. So our general formula for flux is going to be F dot S. That's what's going to kind of be the foundation for finding flux. Okay, so flux greater than 0 is when the net flow is in the direction of n, right? So we orient the surface saying n is the direction of like positive flow, right? And so if your net flow is in the direction of n, so you can imagine for a surface that in some places the flow is one direction and in other places it's the other direction. So if your net amount of flow is in the direction of n, then you have positive flux. Okay, so let's do an easy example. So water flows at 3 centimeters per second through a circular pipe with a radius of 2 centimeters. Find the flux through an elliptical region with n angled at theta radians to the flow. Okay, so we have this is our surface, right? This is like an ellipse. And so imagine there's kind of a membrane here, okay, and stuff is flowing through, and we want to know the flux through the membrane. So n, say like that, for this S. So we're orienting the positive orientation of the surface to say up and to the right, orthogonal to the surface S. So flux is F, so we want to calculate F dot S. And so how can we do that? And then, let's see, n is angle theta to the flow, so this is theta here. So how are we going to compute F dot S? Remember? Yeah, remember there were 2 ways to calculate the dot product, and use whatever's most convenient, right? What would be most convenient here? Magnitudes, product of the magnitudes. Or product of the magnitudes in as much as they're in the same direction, right? That's our whole idea for dot product. This formula kind of embodies that idea for dot product. Product of the magnitudes in as much as they're in the same direction, right? So what's the magnitude of F? Just 3, right? Just 3. Okay, so now what is S? The magnitude of S would mean what about the situation then? The area of this, right? So the area of this. Okay, well there's kind of a, if we imagine, so imagine, I'm going to move it over here. And we can kind of use some right triangle foolery here to do it. So imagine this our circular cross section and this ellipse form a right triangle. See that? And so the same proportion of these sides in the right triangle is the same proportion of the area of the disk and the ellipse. See that? So that makes finding this pretty easy. So what is the area of the disk? And so where's theta? Which angle is theta here? Let's see. Is it this one, the top one, or the bottom one? I think it's the bottom one, isn't it? Let's see. This angle down here is theta. Let me see that easily. Let's see. I don't know. Want to take the time. But the bottom one is theta. But we could trace the geometry through and get that. Okay, and so then this area is what? The area of a disk. The disk is pi r squared, which is pi times 2 squared. 4 pi. Okay, and then the area that we want is S. So how are S and A related by theta? We can use trig to do that. So S times, so S is this ellipse here, and it's like the area is like which side of the triangle? Adjacent side, right? So it'd be S equals, or S times cosine theta equals 4 pi, or A. You see that? So the S is like our kind of like our hypotenuse of the triangle, where the adjacent side is like the area of this ellipse. So then the magnitude of the S vector is 4 pi over cosine theta. But then in the dot product formula, we also have cosine theta. So it turns out to be so what's the moral of the story here? Doesn't really matter, right? Like how this thing is angled. Because you get a bigger, you get less in the direction, but you get a bigger area, so it kind of cancels out. So it'd be 12 pi no matter how you angled your membrane in there. Okay, any questions on that? So the flux through S then is 12 pi. Vector or scalar? Scalar. Flux is a scalar because it's a dot product, right? It's a flow rate, right? Flow rate. Anybody have a question? Yeah, please. Yeah, that's the right question, isn't it? So F is in centimeters per second. And this is in centimeters squared, so centimeters cubed per second. Yeah, volume per second, right? So what volume is going through there per second? So that's how it's a rate. Okay, other questions? We're good? Okay, so let's, there it is. All right, we did it right. Okay, so here's an example. So I want the surface is x equals 1, y from 0 to 4, and z from 0 to 2. And here's F is y minus 1, z 0. So let's look at this visually before we do the problem. Let's talk this through, what this is going to be about. So there's the surface, x equals 1, y from 0 to 4, and z from 0 to 2. And it's living in this vector field here, right? This vector field, is it y minus 1z, is that what it was? So when we're talking about the flux of the vector field through that surface, then what do we care about? We care about, which vectors do we care about? Only the vectors associated with the points on that surface. That's what we care about. All right, so let's look at those. So here's just isolating a sample of the vectors on the surface. Again, if I showed all the vectors associated with the points on that surface, what would I see? It would just be a red rectangle, right? It would just be a red, just be red everywhere, okay? So we just take an array of them to get a feel for what this is like. So now, when it comes to those vectors, what part of those vectors do I care about when I'm talking about the flux then? What aspect of those vectors is important? Yeah. The component perpendicular to the surface. So I'll show both now. So the red is the actual vectors, and then the blue is the components of the red vectors orthogonal to the surface. And so when it comes to computing the flux, the blue is only what I care about. That's going to be what contributes to the flux. Any flow parallel to the surface, which is the rest of those vectors, is going to have no effect on the flux. Right? Flux is the flow rate through the surface, so it's going to be just the perpendicular components, or parallel to the S vector, right? These blue vectors are parallel to the S vector, which is already orthogonal to the surface. So when we do this calculation, are we going to expect positive or negative value for the flux? If what? Yeah, if we orient it to be in the positive x direction, so if the orientation of the surface is in the positive x coming at you, then the flux should be positive, right? Because most of the flow, the net effect of the flow is in the positive x direction. Make sense? So let's do the math and see if that all plays out. So let's sketch it here. Okay, and so flux is equal to? F dot S, right? F dot S. It's the product of the area and the flow, in as much as the flow is in the direction perpendicular to the area, right? That's exactly what F dot does. F dot S does, right? F dot S. Okay, so how are we going to do this? So what's different about this example as opposed to the pipe example? Yeah. What's that? Okay, that's true, but there's something significantly different here. What's that? Okay, so what's that? Or not only direction, but yeah, so what this vector field is a changing vector field. The vector field I gave you with the pipe was a constant vector field, which made this calculation very easy. As soon as I move from point to point on this surface, I've got a different vector in my vector field. So how are we going to be able to solve this? Yeah, so it's about accumulate all the flow rate all over it. So what I have to do that, I'm going to have to take a teeny little area, right? So I can't do the area of the whole S. I got to do a little area at a time where I can assume constant F, right? So that's going to be, we're having a little ds, right? A little ds. And a ds and a little ds. So what's the difference? What is ds, not a vector? What would that be? What's that? What about the small part? It's d capital S. That's the area, right? So that's going to be like a area element, or the area of an element. And what will that be in this case with the plane that we have? Right, so the area would be dy dz, right? It would be dy dz. Make sense? Okay, then what's ds vector? What's that? So how's that different from ds without a vector? So ds vector is what? It's not the surface integral, just the ds. Parallel to the x-axis. So just think about what s was. The s vector was. Now this is just ds. So it's the same. It's the same thing as an s vector, just for a little teeny area, right? So it's still an s vector. So what would it be? So we could write that vector down because of how easy this surface is. So what would that vector be? No. So remember the magnitude of an s vector is what? The area, right? We did that above, right? So the magnitude of ds is ds, right? What was that magnitude? dy dz. And what's the direction of this going to be? X. So the vector will be dy dz 0, 0. So ds is just like a miniature version of what s would be. We know s is an area. So in this case, for this problem, the miniature area would be dy dz. And then ds vector is just a miniature version of the s vector, which we talked about. It has magnitude, area, and direction orthogonal to the surface according to n, how we orient it, right? Okay. So what we're going to do instead of f, so we can't do f dot s, but what we can do is f dot ds, right? So what's f dot ds? And once we can write that down, because for a ds we can assume a little constant. We can assume that f is constant for a little teeny element, right? We can just pick the f at that element. Yeah, so that's a little bit. That's the little amount of flux. Say for that little. That's supposed to be a little rectangle. Let's make it a little bigger. So that has dimensions what, dz and dy, and that's where we got dy dz, and then n, positive orientation, is in the positive x direction. All right, so then f dot ds would be, it would be the flux for just one of those little things, one of those little rectangles, dy dz, rectangles. So how would we get the whole flux? Yeah, so we're going to integrate up all of these. And so what kind of integral will that be? Double. So the flux through the surface will equal double integral over s of f dot ds, which equals double integral over s. What's f? y minus 1 z 0 dot. What do we find was ds? dy dz. Do you see that we have understood the meaning of every single symbol as we've done this, and for an expression? That is going to be this. So this is the easy part of this thing. So when these get hard, you have to hold on to that. You have to know the meanings of every single symbol to make sure that things make sense. Are we good so far? So then we end up getting, when we do the dot product, just y minus 1 dy dz. Y goes from 0 to 4, 0 to 2, and we expect this value of this integral to be, remember from our positive, remember we said the net flow, most of the flow is coming in the positive x direction. So can we do it fast? Y squared over 2 minus y from 0 to 4, is that 8? Is that 4? 0 to 2 zz? Is that 8? Make sure that's right. Y squared over 2 is 4 squared over 2 is 8, minus y is 4. And this is a polynomial, that's why 0 gives 0, but when the limit of integration is 0, it doesn't necessarily mean your integral is 0, right? There's things like exponential functions and cosine functions that give you non-zero values for 0, but because it's a polynomial, it's 0. All right, so yes, check, greater than 0, according to the image that we saw. Cool so far? All right, so now what if we have, so why was this was even easy. It's still, the fact that this was still easy, why? Because this was x equals 1, right? And so that surface was flat and n was just, what? Just 1, 0, 0. So now if we had a curved surface in a changing vector field, then that's the most general case, and that's where it gets harder. Any questions on this? But it's still all the same stuff. So we got a parameterized surface, and our two variables are generically u and v. That might be x and y, that might be r and theta, that might be y and z, whatever we choose to parameterize the surface. And then we need to, like we did in the last problem, we need to cut it up. But when we cut up a curved surface, we don't get rectangles anymore. We kind of get, well, we kind of get like warped rectangles as our elements. But we don't know how to find the area of warped rectangles. Okay, so what we really need is we need a flat version of this little blue element, right? This curved element on the surface. We need a flat version of that so we can actually do something with area. So what's a flat version of a warped rectangle? Almost. More general than that. Doesn't have to be right angles, right? Doesn't have to be right angles. So it's not even a rectangle. So it's like a warped quadrilateral is what it is. So what's a flat version of that? The pink is the flat version of that. What do we get? What's that? It's a parallelogram. It's a parallelogram, right? So it's like a rectangle, but doesn't have to have right angles, okay? It's a parallelogram. So what we need to accomplish this, to get what we need, is we need the tangent vectors. To create that thing, we need the tangent vectors. So for holding v fixed and changing u, we know that the tangent is the partial with respect to u, right? So if our parameterized surface is r, then that vector is the tangent vector for fixed v. So that'd be like the partial of r with respect to u, right? And then similarly, holding u fixed and taking the derivative, we get the tangent in the direction of changing v and fixed u, right? So the partial derivatives ru and rv point in the direction of the contours on the surface. And that's the same direction that these little elements are formed out of, right? So now we need to get the size right. So how do we get the size of these vectors then to match up with the size of our elements? So this should be. So if I take RU and I multiply by du, then that scales the size. If I take RU times du, then it scales the size of that thing to be what I want. And same with the other one. If I multiply the partial of r with respect to v times dv, then it scales the size. Now those two vectors are actually forming the parallelogram that I want. That's trying to be like the warped elements that's actually on the surface. Okay, so what is ds for that little pink? I'll do it in red because it's red. What is ds? Meaning, what is the s vector for that little element, that little flat element? So we need two things for that, right? What do we need? We need, if it's a vector, we need what two things? Direction and magnitude, right? How are we gonna get the direction of that? Okay. Cross product, right? Cross product is gonna be orthogonal to those two vectors, so we do cross product of those. And then what about the magnitude of, what do we need the magnitude of ds to be? So what is the area of a what? And then remember how we got the area of a parallelogram? Okay, that's honest. No, remember area of a parallelogram? Remember? Yeah. No, from calculus. What we learned this semester. Yeah, it was the magnitude of the cross product was the area of the parallelogram formed by the two vectors, right? Remember that? So ds, so this is all about cross product, right? It's all about cross product because the direction of ds will be the cross product of those two vectors, and the magnitude of our little ds will be that area, which is the magnitude of the cross product. So let's blow that up here. Again, this should be dr or dv and du. So dv, rv, and du. And so then ds is the vector, is the area vector for that little parallelogram element, which is trying to be like the curved element of the actual surface. And when things get small, those flat parallelograms will reproduce all the blue elements when things get small. So area of the red parallelogram is? It's going to be the magnitude of the cross product of that thing. So that then is what we could also call ds. So I did the cross product there, and then the du and the dv are just scalars, so we can just bring those out, right? Those are just scalars, so we just do ru cross rv times du dv. And that's just ds without the vector, right? That's just the area of that parallelogram. So what we're really after is flux, but what we just kind of discovered is, as a side thing, what could we get if we did a double integral of ds over the whole surface then? What would we get if we did the double integral of just these ds's? Not f dot ds vector, but just the ds non-vector. If we did the double integral over a surface, what would we get? We just get the whole area of the surface, right? Because these are little area elements. So as a little side note here, surface area would just be the double integral over s of ds, and we get surface area in R3. And so then, how would that be calculated? So you'd parameterize your surface. U and v are your variables, the two variables that you picked, and you do ru cross rv, and do that, and the magnitude of that, du dv, and so you'll end up with a double integral that will get you the area of your surface. So that was just a useful little tangent. What we're really talking about though is flux. So let's talk back again about flux. So our point area vector, then we can say that ds is n ds. So n being a unit normal vector, right? So n is a unit normal vector, and ds the area vector. So we already talked through this. So the normal vector n unitized would be what? It'd be the cross product unitized. So it'd be ru du cross rv dv be that vector, and then if we want to just have it be a unit vector, it would be what? Divided by the magnitude of that. I want to write it again. But then what's ds? That magnitude again, right? ds is the magnitude. So you get a cancellation, right? So you get r cross u, r cross v over the magnitude, then times ds, which is the magnitude, so then you times du dv. So then our point area vector ds becomes ru cross rv dA, right? dA would be dx dy or rd theta or whatever. Okay, I'll just pause for a second here. Did I lose anybody? So make sure we know what everything means and every step along the way here. This is n. this is ds. Those go away, and so then we get an easy version of the ds vector. What's the ds vector? That's the point or the element area vector, right? Maybe element, say element. Little parallelogram, right? A teeny little parallelogram that has both the magnitude of the area of that parallelogram and the direction is orthogonal to that parallelogram, and so orthogonal to the surface. Okay, so then we know the flux is going to be the double integral over S of f dot ds. And we have what ds is now, the ds vector. So it's f dot ru cross rv dA. Okay, so we're going to be using that a lot in examples, but you don't have to just know the formula and be able to do the examples. The setup is really important because of it used so much of what we learned this semester, right? So how you get this formula is just as important as being able to use it, is what I'm trying to say. If you have a question, don't hesitate to ask. If I lost you somewhere. Okay. Are you sure? All right. So let's do an example. So I want to find the flux through S, which is the part of z equals 4 minus x squared minus y squared that lies above the unit square in the xy plane, if f is this, xy, yz, zx. So we have a curved surface, we have a complicated vector field, so this is an example of the most general case for flux, right? There's nothing about this making it easy, like the previous examples we've done. So let's sketch that. What is 4 minus x squared minus y squared? It's not a cone. Paraboloid, right? So this is like z equals x squared plus y squared, but down 4. So it's paraboloid. And then over the unit square. So we only want the part of it that is above the unit square. So maybe this is 4 up here. So what's that going to look like? Over this line, x equals 1, it's going to keep going down, right? Curved. And then over y equals 1, same thing. Like this. So it's going to be this like sloping, curved down part of the paraboloid over the unit square. And so the flux is equal to flux through S equals double integral over S of all the point fluxes, right? Taking every little f, so here we got an f like this. I think it started red, right? Red first. So maybe that's f at that point. And what do we care about? The part of that is, we want the part of every force vector on that surface that's orthogonal to the surface or in the direction of n. So we'll say n is upward orientation. And so then we're going to accumulate all those f dot, so if this is the part of f in the direction of s, we're going to accumulate all those f dot ds's for that whole surface. And we said we know that that is what? Ru cross Rv dot du dv. Is that consistent with what we said on the last screen? Did I forget the F in there? Oh, that's why I asked. Dot F. That's kind of important, right? All right, now do we have it? Look, dot product and cross product, right? Cross product because the parallel vectors in our parallelogram, cross product gives us the direction of S vector, and then dot product, we want to take the amount of F in the direction of S. So dot product also. Is it right? Okay. Or was it F dot ds? Is that why you're, is it this way? Yeah, that matters. Well, then no, the dot doesn't matter. Dot product doesn't matter. So you can put that first. Cross product matters. Order matters in cross product because you get the opposite direction. But dot product doesn't matter. So F first doesn't matter. All right. So what do we have to decide? What do we have to figure out here? We got to parameterize the surface, right? We got to pick what our u and v are. Possibilities for u and v? X and y. Any other possibilities? Yeah, we got a paraboloid, so maybe r and theta. So we got a decision to make. So we want to be forethinking here. What's going to be more convenient? So what is that really about? So in terms of the convenience of a double integral, picking x and y versus r and theta is really about what in solving the double integral? But in terms of solving the integral, where is that?
It's about the area that it's in. The area
the project. You think same? You mean the projection?
Yeah.
Isn't it about the projection that we have? Isn't it about how we're going to set up our limits of integration, which is going to be the projection, right? So which x, y, r, theta? X, y, right? X, y. We don't want to try r and theta for a square in the polar plane, right? So no. So definitely want to do x, y. So what? So we can go 0 to 1, 0 to 1 for our limits, right? Okay, so we want to then, what we need r x cross r y. Okay, so we need to first of all, we need to parameterize the surface in x, y. So how are we going to parameterize? Okay, like falling out of bed, right? This one's easy. We like parameterizing in x and y, especially when z is a function of x and y, because we can just write it down, right? Our two x and y as our two parameters. Z is just whatever z is. So now, what's r, partial of r with respect to x? 1, 0, minus 2x, partial of r with respect to y. 0, 1, minus 2y. Cross product is going to be 0, positive 2x, is that right? Positive 2y and 1. If you do the determinant, you get 2x, 2y, 1. Okay, so now we're home free. So just because you'll probably normally be doing f first, because that's the way it goes, we'll make it f first. So f is xy. Now here, remember, now we got to write f in terms of our two parameters. So it's going to be y times 4 minus x squared minus y squared. And same thing again, 4 times x squared minus y squared times x dot 2x, 2y, 1, dx dy. So now we know our u and our v. And x goes from 0 to 1, 0 to 1. So that double integral is not hard, it's just long. It's just tedious. Not worth spending the class time doing, but you do the dot product and you get a big polynomial of x and y. And you all know how to do double integral first with respect to x, then with respect to 1. And that would be the flux through that part. This is S through S, which is that part of the paraboloid. Any questions? I'll leave it up for a second if you want to ask me a question on your way out.